Back from
Yeah, Keith, we gotta run back
Yeah.
Bring football.
Let me just go through, guys. Let me go through the calendar. So we're going to start 8.1 today. Area between graphs. Not a long unit, so we're just going to have a quiz, but over this unit. I think this is the most important part here. If we can figure out, if we can fully understand how to work area between graphs, either from a vertical perspective or from a horizontal perspective, then this is the foundation. Because if we're good with this, then all this is just going to feel very easy, because all we're doing is just setting it up correctly. If we can set it up correctly, the rest can just be used. We can use a calculator to find everything else. So this is really the foundation here. So I think this is the most difficult day, because there's we just have to figure out the orientation when we go through our formula. But once that is set, then it's the same process here with just an additional different formula for volume, but we're just adding to the same concept for area. Okay, there's homework tonight, but I will check this homework on Monday. I'm working on the key, so I probably won't have that key ready until the weekend. So I will send out a link and make sure, I'll send out a reminder, make sure that so you guys are able to check your answers. Okay. Quiz is tomorrow. So when you guys come and get your phones, you guys can pick up worksheet 2, key. So you guys picked up worksheet 2 yesterday at the end of class, and I have the key ready. I also have it on the website. So this afternoon, I'll be available if you want me to go over any of those problems. But I think if you're able to go through worksheet 1 and 2, it's the same types of problems like that. So hopefully you feel ready for tomorrow's quiz. Make sure you bring your calculator as well. I'll send out a reminder this afternoon. Okay. So next Wednesday is senior service day. So we'll just push this back here. So we'll do volume cross section on Thursday, and then we'll have quiz review on Friday. And then we'll have the quiz either Tuesday or Wednesday when we get back from break. Okay. All right, so let's go to so we've already kind of know how to find area, right? Area is just the integral of the function, but we talked about how with displacement, sometimes we may end up with a negative value. But if we're talking about area, to ensure that we're always getting a positive value, we do this. We do top graph minus bottom graph. Okay. Before, we never really had a bottom graph. We just did integral of top graph, because the bottom graph was always just the x-axis. Okay? It was really always just -0, and if the graph is below the x-axis, that's why we're getting a negative value. But if there is a graph visually above the other one, then if we do top graph minus bottom graph, then we're always going to ensure to get a positive number, and that will be guaranteed to be something that is exactly the area. Okay, so here, let's say f of x is the graph that is higher, at least between the bounds, and then g is the graph that is below. So what we can do is imagine that we're adding infinitely thin rectangles from one end to the other. Okay, and the top of my rectangle is touching the F, The bottom of my rectangle is touching the g function. So we're just going to follow the formula here. So it's the antiderivative of my left bound to my right bound. My left bound of the shaded region is from A. Right bound is B. So it's a definite integral from A to B of f of x minus g of x. So f of x minus g of x is my height component. Dx is my width component. And then width times height gives me area. Okay, so this next example here, if I want to find the area of this region, then this line, my bottom graph is just the x-axis. So integral from A to B, f of x technically is minus 0 dx, but we can drop that 0. So that's why we've always left out the 0, right? Because it's always whenever we did integral before, it's always with the x-axis in mind. Okay, let me have you create an example 2, part B here. So if I want to find the area of this region here, definite integral from A to B, my left to right bound. What's the graph on top in this case? 0, right? So if I draw a horizontal, if I draw a representative rectangle to represent my height, then the top of my rectangle is touching the 0. The bottom is touching the g of x. So it's 0 minus g of x dx. So if we always do top minus bottom, we're always going to ensure that whenever we plug in the calculator, or if we were to work out the integral by hand, we're always going to get a positive number in return. Okay. So let's look at example 3, where we're going to be working out a problem by hand here. Find the area of the region bounded by y equals x squared and y equals 2x plus 3. So y equals x squared is the parabola that you see below. And the 2x plus 3 is the linear graph that you see above. So first thing we do is we want to find the bounds. We want to find the x and y bounds here. They're not given to us explicitly, so we have to kind of work it out by hand. So the way we find those bounds, in this case, we're just going to find the points of intersection. And if we find the points of intersection, then this will be the left bound, and the right bound is going to be where they intersect again. So the way you find the points of intersection is we set the equations equal to each other and solve for x.
You don't have to worry about extraneous solutions.
No. Mm-hmm. We bring everything over to one side. Factor multiplies to be -3, adds up to be -2. -3 and 1. We solve for x, we get 3 and -1. So we have the bounds of our shaded region from -1 to 3. So now we can set up our area formula, identify the top and bottom functions. So I'm just going to draw a representative rectangle here. The top of my rectangle is touching the linear. The bottom is touching the curve. think it's always a good idea to protect the bottom function with a set of parentheses. Even though there's only one term here, it's not going to make a difference. But whenever there's more than one term, we always want to make sure that we don't forget that the negative is going to distribute through that bottom portion. Okay, so this we can work out by hand. Once we get to more complicated problems, we're just going to make the calculator do it. But here we can work this out by hand. Power rule for each of the terms. And then we can evaluate the bounds, upper bound first. Now, if this problem happened to show up on the FRQ on the non-calculator portion, then you can leave your answer in this form. Okay.
Did you mean to put 3?
Oh, sorry. Say it again.
Did you mean to put 3 instead of 2? Did you change the?
Oh, sorry. Yeah, sorry. This should be 3. Thank you. 3 square root of 3 times 3. Yeah, you can leave your answer in unsimplified form, but for now we can say 32/3 units squared to remind us that this is an area unit. Okay, so I think we're used to this orientation, top minus bottom, if a graph is above the other graph. But we can also find an area if a graph is to the left or to the right of the other graph But a lot of times these are not going to be functions, but we can still find the area of the region between the two curves. Okay. Everybody okay? First page. So if I have a horizontal orientation, horizontal rectangles between curves. So now instead of stacking vertical rectangles from left to right, imagine you're stacking horizontal rectangles from bottom to top. So now these are not going to be functions anymore. These are going to be equations that will not pass a vertical line test, but we can still create these equations in terms of x equals f of y, right? So this can be a function in terms of y here. So if we want to create equations that is in terms of y or x equals, so if I can isolate x equals, then I know that I have an equation in terms of y. I take the graph on the right, I take the graph on the left, and then my bounds need to be from the lowest y value to the highest y value. Okay, so everything is kind of flip-flopped here. This is not the orientation that we're used to, so this is the one that we're going to have to require a bit more work to get comfortable with it. So here, if I want to find the area of this region here using the horizontal orientation, then I would say the integral from C to D, because those are the lowest and highest y values. And I do right minus left. So the right endpoint of my horizontal rectangle is touching the f of y. The left endpoint is touching the g of y. So I do f of y minus g of y. dy. So let me show you what that looks like with example 4. So let's say we had these two equations here. 1/2 y squared minus 3, that's this parabola that's opening to the right. And then you have the linear equation x equals y plus 1. If we want to do top minus bottom, the issue with top minus bottom is that we're not able to create one equation that's going to get us there, right? Because this rectangle here it's going to have a different top and bottom versus a rectangle here. So we could do top minus bottom, but then we have to split it up, right? So top minus bottom in this region will be this curve minus this curve, but then there's going to be a switch. Once we get past this point, then it's going to be the curve minus a line if we want to do that. So we can do top minus bottom. We have to separate into two separate regions. But if we do right minus left, then there's more consistency there. We can just rely on one integral to help us get there, because no matter where I draw my representative rectangle horizontally, right, if I slide this up and down this region, my right endpoint is always consistently sitting on the line, and my left endpoint is always consistently sitting on the curve. So I know I can just rely on one integral to produce the area of this region. But if I want to do horizontal rectangles, then everything has to be adjusted. My bounds have to be in terms of y. My equation has to be in terms of y. So this one is set up nicely because this is x equals y plus 1. They already wrote that equation as x equals. And here, this is x equals 1/2 y squared minus 3. So they're both in the proper form. If they're not, we'll have to rewrite it. And that's something that we're going to practice on the next page. But this is a little bit easier. Everything's set up for us. Okay, we're going to set equations equal to each other and solve for y so that we can find the upper and lower bounds that we can use for our C and D here, or our low and upper bound in terms of y. Okay, so I want to solve this by hand here. Easier to do a quadratic without that coefficient of 1/2. So what if I multiply everything through by 2 here? Multiplies to be -8, adds up to be -2. So 4 and -2. So my area is just the depth integral from lowest to highest y value from -2 to 4. -2 is down here, 4 is up here. Right minus left, the right endpoint of my rectangle is touching the line. Left endpoint is sitting on the curve, yes. You can look at the graph, but sometimes the graph may not have all that information. But you will have your calculator, so if you're not finding the bounds on the chart, then use your calculator to find those intersections. Okay, so we do right minus left here. Now, if for some reason you got the right and left flip-flop or the bottom and top flip-flopped, what answer or what would you what result would you get that would tell you that you got those two mixed up? Yeah, it should be a negative version of your answer. So if for some reason you got a negative answer, and then you can just turn that negative to a positive. You don't have to go back and redo the problem. It's just, okay. I mean, you're still getting as long as you know how to adapt. So you're not going to, if you got the wrong order, you can still adjust and get to the right answer without having to redo the whole problem. Okay, so it's power rule, but it's a little bit tedious having to get all those terms separated and then do power rule. But it's not hard. It's just after we do these types of problems, we're going to go to our calculator because I care more about, okay, can we set up the equation here more so than doing all the power rule steps. Now, there are some problems that you have to work out by hand. And if you do, typically there's use substitution involved. So, but we'll get to those FRQs later. But okay, so the bottom of the page, we can do top minus bottom for our two graphs there. Represent the area of the shaded region to the right using integral notation. Can I rely on one integral to get to the area?
No,
Because why?
top and bottom flip.
They're flipped, right? So if I do top minus bottom for the entire interval, then I'll probably get a negative number. Or I'm not going to get the true, I may get displacement, but I'm not getting the true area. So we have to split this up into two separate integrals, right? There's the top and bottom for this region, and there's a separate top and bottom for this region. So see if you can create and write out the two integral notations that will represent the true area of the shaded region. Okay, that makes sense here. F of x minus g of x for the first, for the left interval, and then g of x minus f of x for the second interval. Okay, let's go to page 3. Okay, you're gonna need your calculators here. So this is a area FRQ problem. This is just one. This is an older FRQ problem, but I made the same diagram. I copied it 4 times over so that we can kind of explore all the different variations of finding the area of S and finding the area of R. I feel like this is the most important thing here. If we can figure out how to do this and you're comfortable with this, then the rest of the unit is a breeze, because the hardest part is just figuring out the orientation and the bounds and matching all that up. So, and by the way, the key is on the next page. So if you're ahead of me, then feel free to check your answer there. Okay, so let's read the problem here. It says, let R and S be the regions in the first quadrant shown in the figure. Region R is bounded by the x-axis, the graph 2 minus x cubed. That's this curve on the left here. And y equals tangent of x. Region S is bounded by the y-axis, 2 minus x cubed, and y equals tangent of x. So part A, find the area of S. We're going to find the area of S. We're going to do it in both orientations, so we can kind of get that practice in. There's one that's going to be easier than the other, but it's good for us to just be able to work from both perspectives. So we're just going to focus on S for now. Okay, let's do the easier version first. Okay, I'm going to shade in region S. we can do top minus bottom here because if I draw a vertical rectangle, no matter where I slide this vertical rectangle, the top of my rectangle is always hitting the same curve and the bottom is always hitting the other curve, right? So there's not a sudden switch. So I can rely on one integral to find the area. My bound is going to be from 0 to wherever this intersection is. Okay, so we're going to make the calculator find the intersection for us. So you'll go to y equals. So for y1, I'll type in tangent of x. Make sure that you are always in radian mode. If you're in degree mode, you're never going to be in degree mode. Okay, so it's always in radian mode. But radian mode, degree mode is only going to impact you if you're dealing with trig. So I have tangent of x and 2 minus x cubed. If you do zoom 6, it'll take you to a negative 10 by 10 window, which is probably a lot more than we need. This is just going to be a very small region in the first quadrant, but I think it's good just to start off with zoom 6. It's just this little sliver of area here. So we're going to really zoom in on that. The way I like to zoom in is do zoom box, because then you can just section off exactly where you want to zoom in without having to change all your window values. So I'm going to just scroll to where I think I want the upper left corner of my box. Hit enter once, and then you can just scroll until that box forms. Don't hit enter again until that box is completely finished. Once you see the box in front of you, then hit enter a second time. And you should get a picture that matches the graph pretty well. So let's find the intersection of the two graphs. So do second trace, intersect. So second trace 5. Now you're just going to put your cursor at a point close to the intersection. Don't put the cursor directly on the intersection. The calculator will find it for you. So just pick a point that is relatively close to the intersection. Hit enter. And the calculator is going to say first curve. So it just wants to know which two curves are you dealing with. I know there's only 2 here, but they still want you to tell the first curve. And then if you toggle using up and down arrow, you should be able to see a blinking cursor on the other curve. Hit enter again. And now the calculator will find the intersection closest to those 2 points that you identify for it. I know that we only need the x value, but let's go ahead and write the x and y value. That will be helpful when we get to part B.
Three decimal places.
Yeah, 3 decimal places is a good start. Okay, so now the area is simply the integral from, what's my left bound? 0 to, good. Okay, what's the top of my rectangle touching? So that's going to come first. Minus, look at the bottom of your rectangle is touching the other curve. Yep. And now let's just make the calculator do everything for us. So do math 9. Take advantage of the y1 and y2 that you've entered in. So I'll go from 0 to 0.902. My y1 is tangent of x, so I'll do alpha trace y1 minus alpha trace y2 dx.
Your y1's tangent.
I'm sorry. Yeah, my y1 is tangent. Yeah, so if you have a different order, then do the appropriate. I'm sorry. Sorry, 2 minus x cubed. My bad. So I should have done y2 minus y1 since I have my order flip-flopped. Okay, so you guys get 1.161. Okay, so that's my area. Okay, so now we're going to force ourselves to do the same region from a right minus left perspective. I mean, you know, on the AP exam, if you saw this, you would always go to do top minus bottom. But I think for our practice purposes, it's nice to know how to go back and forth between the two variations. Now, if I want to do right minus left, everything has to change. My bounds have to change. My equations have to be in the proper form. Notice that this is all y equals, right? So if I have y equals and x is on the right side, this is perfect for top minus bottom. Okay. But if I want to do right minus left, then I have to get my equation in terms of y. So a good way to see it is if you can get your equation to look like x equals, and all the y's are grouped together on the other side. So if I want to do right minus left, what do you notice here? Can I draw one horizontal rectangle and slide that up and down and let the left and right hit all the same points? Not quite right. There's an upper region, but once I get to this intersection, then my right endpoint is going to switch. So how many integrals do I need? I need 2, right? I need one that can handle the top portion and the second to handle the bottom portion. Okay.
You know where to draw the rectangle.
It's just a representative rectangle. Yeah. So you can put it a little higher than mine, a little below than mine, but it's all, we know that anything here will be consistent, right? From here to here, my left and right endpoint is always consistently hitting the same graph. Okay. And that just creates a representative rectangle. Okay, my equations have to be in a different form. So how can I write y equals tangent x in a form in terms of y here? Yeah, inverse, right? Or arctangent. Right. And then let's also rewrite the equation in the proper form. Y equals 2 minus x cubed. If I want to solve for x, I get x cubed equals 2 minus y, cube root both sides. My bounds have to be in terms of y as well. So I know this y value is 0 because that's the origin. I have the same order pair here. I'm going to use that y value. And I also need the y value here. For this one, we can just make the we can plug in the calculator, right? Because this is y equals 2 minus x cubed, so that's the y-intercept. So if I replace sorry, y-intercept, this is my y-intercept, so I can replace x with 0. So what's my y value there? If I replace x with 0, 2 minus 0 is 2, right? So All right, so let's set up our integral here. Let's start with the bottom here. Let's do the bottom region. We want to go from bottom to top in terms of y, and then right minus left. Every equation has to take on the form of x equals. Okay, what's my lower bound for my bottom region? 0 to what? Good. We want to choose the y value, right? Right minus left. What's the right curve of the bottom region? Let's see, is that right? No, this one here. This is the arctan y, right? Okay. Minus, okay. What's the equation for the y-axis? 0. So that integral will take care of that bottom region below that dotted line that I created. The upper region, from where to where? Lowest y value to highest y value. To 2. Right minus left. There's a switch here, right? What is the right endpoint of my rectangle now touching? Yeah, the cube root of 2 minus y. Minus still y-axis. Yeah. Okay, so we're going to enter this in the calculator and see if we get the same answer. We should, right? I mean, I understand that on the exam, you're never going to do it this way. You're going to do it this way. But it's good that we know how to do it this way, because sometimes we're forced into a problem that we have to do it from a y perspective because it doesn't work on the x side. So it's nice to have the problem where we can go back and forth and just confirm, try all the different variations for practice purposes. Okay, now again, in your calculator, I know you're seeing this on paper as y, but in your calculator, you're always using which variable? Always use x, yeah. On paper, you're writing it in terms of y, but don't use any other variable in the calculator except x. I'm going to let y3 hold my arctangent of y. And then I'll let my y4 do the cube root of 2 minus 1. Cube root is math 4. If we do math 4, you'll see that cube root show up. It's right. And a good way for you to ensure that you are in the proper form is if you're doing everything in terms of y, the left side will look like x equals. Yeah. So it'll always look like that setup.
Yeah.
And then for functions, it'll always be y. Okay, enter in your calculator, and we should get the same area. I got 0.664 plus 0.4965, which adds up to be the same area of 1.16. Okay, any questions with the region S? Okay, let's do region R. Same diagram. Let's do it from right top minus bottom perspective. So if I want to do region R, top minus bottom, can I rely on one integral to help me get there? No. Okay. So if I draw a representative rectangle, and if I were to slide that rectangle from one side to the other, that top is going to have to switch, right? At the intersection, it's going to switch to a different curve. So I don't have the same top function for the entirety of the region. So I need two separate integrals if I want to find area of region R. The nice thing about top minus bottom is we can keep everything the same. There's no need to rewrite our equation. Again, we're going to make use of the order pair of that intersection order pair. But we're also going to need that x-intercept. Right, so if I set 2 minus x cubed equal to 0, I can use second trace 0 to help me find that x-intercept, or I can solve it by hand. What's that x value going to be? Mm-hmm. Okay, so let's do the left region first, followed by the region on the right. So the left region is from 0 to what? 0.902. What's the top curve of my first region? Tangent x. What's the bottom? What's the bottom of the rectangle touching? Y equals 0. Yeah.
Y.
Yeah. But yeah, the x and x-axis. Okay, the second region here, I know it's a little bit small. What's the top of my second rectangle touching? 2 minus x cubed. Top minus bottom, the bottom of my rectangle is touching the x-axis, so 0. And what are the bounds going to be here? 0.902 to this cube root of 2, or you can do the decimal version of that. Hey, make sure you're in radian mode. Enter that into your calculator.
Put that 0.
No, I just want to show you that that's what the bottom function is. You can drop that 0 out. I just want to show you that I'm following the formula for top minus bottom. Okay, any questions with top minus bottom for region R? Okay, let's do region R from a right minus left perspective. This requires us to change our equations, but we've already gathered everything we need from part B from above. So what's nice about right minus left for this problem? Yeah, all we need is one integral, right? There's no sudden change with either the left or the right bound, or left or right graph of my rectangle. What are my bounds going to be from 0 to what? 0 to 1.266. So this one's going to feel a little cleaner than the one above because everything that we need is, and also there's only one integral needed here. So the right endpoint is sitting on the cube root of 2 minus y. The left endpoint is sitting on the arc tangent of y, or inverse tangent of y. Insert that in your calculator. Again, you're using X's in your calculator, but we should get the same answer. Okay, if you feel good about this, I promise you the rest of the unit is gonna just be an extension of this. It won't feel any harder than this. The hardest part is being able to know how to rewrite the equation in the proper form and then knowing to look at the y values for your bounds. I think that's the hardest part of this unit, because when we get to volume, it's just the setup, right? If you get the setup, then the rest of it is just formula. Okay, there's homework, but it's not due until Monday. Prefer that you guys spend tonight practicing and reviewing for your quiz. All right, come get your phones, and then I have a worksheet 2's key that you guys can pick up. Hopefully you guys can use tonight to use worksheet 2 as a review to see, just to kind of make sure you're really ready for tomorrow. Let me know if you do not have a copy of worksheet 2, blank copy. I'll give you that. If worksheet 2 blank copy is here.
I didn't have all my. Yeah. But you have time to I'm making sense to the song.
Oh, yeah.
I was feeling about this. What they're saying
I'm sorry.
Oh, all right.